Hello, my name is Patrick Wheeler. I'm responsible for product management of Oracle Multitenant. This is a new architecture for consolidating databases and simplifying operations in the cloud. Today I'm going to discuss several subjects around Oracle Multitenant. I'll start by what was our thinking as we redesigned our database. After all, we've had the best database for many years, it's no secret, but we really did have to redesign our database as we consider the requirements of the cloud. I'll go through our thinking process and then we'll get into some detail about this new architecture. Having explained it, I can then move on and describe some of the new capabilities that are enabled, and then come to a very important topic, managing shared resources. When we consolidate a lot of applications into a single space, it's important to understand how these different applications are going to contend for the shared resources in the system. Of course, at the end, you'll want to know how to upgrade to multi-tenant. I'll explain that and discuss some of the prominent use cases we see for this new architecture. But first of all, let's talk a little bit about the business pressures for consolidation. Well, there's a combination of pressures here. On the economic side, there are requirements to simplify, to reduce license costs, to reduce floor space, electricity costs. On the operational side, there's a demand to realize the promise of cloud computing. We're talking about flexibly adapting to changing workloads, a move from custom applications to a set of standardized services, possibly self-service provisioning of applications. So the requirements that this informs are that we have to have isolation of tenants in this consolidated environment. It's got to be easy to adopt. It can't just be some pie in the sky. But we want to be able to manage many applications as one, many application databases as one, but to retain granular control where appropriate. But ladies and gentlemen, this presentation is about consolidation. So the question isn't so much why to consolidate as how to consolidate. People have tried many approaches to consolidation over time. They might have tried virtual machines. And with virtual machines, you've taken individual, formerly standalone servers and put them into a VM and consolidated all of those into a great big server. But what we find is that you've replaced physical sprawl with virtual sprawl, and virtual sprawl is still very expensive to manage. The other downside with virtual machines is that in each individual virtual machine, you replicate the overheads of the operating system and the relational database management system in each VM. And that replication of overheads is inefficient. So a more efficient approach to things is to get a single big server with a single copy of the operating system and pile in multiple copies of the database into that. We might call that dedicated databases or stacked databases. And I'll talk more about this in a little while. But we found that the densest that we could consolidate databases in prior architectures, at Oracle 11g and previously, was with an approach we call schema consolidation. And in schema consolidation, we get a single large server and a single database. And each of the individual applications is hosted in a dedicated schema or table owner within that architecture. Now, if you can do that, you achieve great consolidation density. But it's a big if, because to be able to achieve schema consolidation, you have to overcome various obstacles. There are namespace clashes. There are some security problems. But if you've done it, you've achieve great consolidation density in terms of the number of applications you can host on a specific server. And you also have the ability to manage many as one. In fact, you've got no choice because everything is stuck together in one database. When you need to patch it, all the applications get patched, whether they're ready or not. If there's a leader who wants to move ahead, sorry, you're stuck. You have to wait until the whole crowd can move with you. Now, in Oracle Database 12c, we move to a new architecture, Oracle Multitenant, in which we take all the advantages of schema consolidation, but we eliminate all of the disadvantages. So we retain the flexibility to manage these environments individually, and we'll come to that in a little while. To do this, we've replaced the individual schemas with what we call pluggable databases. So this is the multi-tenant architecture. Now, before I get into the details of the architecture, let's consider that middle option, the dedicated databases. And let's understand what happens every time we create a new Oracle database. What do? We create a set of files to store the data in. We kick off a series of background processes to manage this data. And there's a dedicated memory environment we call the SGA. And we replicate this every time we create a new database. And as we do so, the resources in the system are quickly consumed. So with Oracle Multitenant, what we do is we replace all of these dedicated databases with what we call pluggable databases. We consolidate them into a single operating environment with a single shared set of background processes and a single shared memory requirement, and we call this the new multi-tenant architecture. So before I describe the new architecture, let's review the architecture of Oracle Database 11g and prior architectures. What happens when we create a new Oracle database? What do? Well, we create a set of files to store the data in. We have a series of background processes to manage the data and a single shared memory area called the SGA. And we replicate this for every database that we create. And as we do this, we quickly consume all the available resources in the system. So in Oracle Database 12c with Multitenant, we replace these replicated environments with a single consolidated database into which we plug these various pluggable databases. And as we do this with a single set of background processes and a single shared memory area, we have much more efficient use of the resources. Now, talking now a little bit more in detail about the multi-tenant architecture, it's important, I think, to start by defining terminology. You've heard me mention pluggable databases. Now, there are two parts to the term pluggable database. There's pluggable, which is new, and there's database, which is familiar. So before we talk about what's new and exciting with Oracle Database 12c with Multitenant, let's review what hasn't changed. A pluggable database is a fully functional, self-contained Oracle database. From the point of view of an application, it hasn't changed in any way. And that's very important because it means that it's extremely easy to adopt this architecture. Now, we introduced this new concept called the root, into which we plug these various pluggable databases. And the whole consolidated unit we call a multi-tenant container database. That's a mouthful, so we'll abbreviate that CDB. And the pluggable database we abbreviate PDB, and root is root. Okay, so that's the new terminology. Now, the pluggability comes from the fact that you can plug a PDB into a root, but you can just as well unplug it from the root and move it to a different container database. And to do so, this is just a metadata operation. You can move a database from one container to another. That turns out to be an extremely valuable thing to do, and we'll see why later on in this presentation. When you move a database, a PDB, from one container to another, it's a matter of moving metadata. So on shared storage, this is an extremely efficient operation. It doesn't matter if you're moving a 50 terabyte database or a 50 gigabyte database. It's just a metadata operation and can happen extremely quickly. The orchestration for Oracle Multitenant is very familiar. It's SQL. Look at these SQL statements. You don't need to memorize these necessarily. But if you've never seen Oracle Database 12c, but you know your way around an Oracle database, you already know how to use this. The unplug statement, alter pluggable database. Unplug into, and the XML file is what we call a manifest. It describes the unplugged database, which will later in the second step be plugged into another container, or create pluggable database using, and there's the XML manifest file again. So the key takeaway here is that SQL is the orchestration engine for Oracle Multitenant. Now, this is our goal. Let's describe some of the problems that we had to overcome to be able to realize this goal. And I'll start this by describing what happens when you create an Oracle database in the prior architecture. You create a brand new database, and there it is, an empty database. Except that it's not really empty, because by definition an Oracle database and a relational database has a structure in which its own structure is defined. That is called the metadata dictionary. And I'm trying to represent this on this slide between the dotted line there, the little red dotted line. Above the line, if you like, that's the way the user data goes. There's none of that yet. Below the line is the metadata dictionary. So the empty database has the metadata dictionary with rows defining the structure of the Oracle database. Okay, now let's add some customer data. Customer data goes above the line in customer data tables, the definition of which are stored below the line also in the data dictionary. And over time, as the customer schema expands, we get more and more data above the line, and correspondingly we get more and more metadata rows below the line, intermingled with the Oracle data dictionary definitions in the metadata dictionary. And that's worked fine for all these years, but it is an obstacle to pluggability. This was one of our architectural goals, if you remember. To be able to unplug this database now, we have to separate row by row this data. And this is something we wanted to overcome. So looking at this a different way, now we have what was formerly below the line in pink there. That's the customer data. And on the grey side, we've got the Oracle metadata dictionary. And there you see the red rows representing the structure of the application data, intermingled with the grey rows representing the structure of the Oracle data dictionary. What we've done in Oracle Database 12c is to separate these two. Now we have two copies of the metadata dictionary. The one at the bottom contains only the definition of the Oracle database itself, and the one in the Pluggable database above contains only the definitions of the customer supplied schema objects. Not strictly true, because to be able to deliver on something we call the PDB non-CDB compatibility guarantee, that is that you can't tell the difference between a pluggable database and a non-CDB, the old architecture, we need to be able to support the situation where a customer might do a query against the data dictionary. And they'd expect to see definitions of their own self-defined objects, but they'd also want to see the definition of the Oracle objects just as they would in a non-CDB, a database in the old architecture. Now, to be able to deliver on this, we provide in the pluggable databases metadata dictionary what we call stubs, references to the actual object which is stored in the Oracle data dictionary. So for example, if you've got an object such as DBMS SQL defined in the Oracle supplied data dictionary, we have a little pointer in the pluggable database metadata dictionary to say, oh yeah, DBMS SQL, that definition is down there. So we call this innovation the horizontal partition of the metadata dictionary. And through this key innovation, we deliver in-database virtualization with Oracle Multitenant. So a little bit about the dynamics. Now we've got a single shared set of background processes and a single SGA shared by all of the pluggable databases plugged into it. The PDBs, the pluggable databases, see only the objects in the SGA which are relevant to them. This is how we deliver the tenant isolation. And the foreground sessions connect only to data that's appropriate to them. Now let's move on to scalability. Scalability is one of the key goals that we had with the multi-tenant architecture. And we've delivered this by having this single set of background processes and this single shared memory environment. If you think about what happens when you start an Oracle database, there's a certain amount of resource which is consumed just by starting the Oracle database. You can think of it as running your car in idle. You've started off all these background processes, you've allocated all this shared memory. With a pluggable database, every time we add a new database, all we do is we require an incremental amount of resources to support that new application load. As we plug in a new database into the consolidated environment, we see another small increment, but the point is that the overhead has already been paid for. We can think about this very simplistically with what I call multi-tenant math. Let's assume that you've got an unconsolidated system running at, let's say, 60%. And let's say we're running on 5 cores. Okay, we can count those on our fingers. So here's 5 cores, and we're running at 60%, let's say. So we'll take 2 of those cores away. So that means we're only really using 3 of those cores. But very simplistically, we might say that one of those cores is required just to support the operating environment, the operating system perhaps, and the RDBMS background processes. Let's take that one away as well. So that means that we only need 2 cores to support the application processing load. Okay, so now let's consolidate. And let's consolidate into a server, let's say, with 10 cores. Okay, 10 cores. Now, you'd be a fool to try and run this system at 100% load, so maybe we'd aim for about 70% load. Let's take away 3 cores. There we are, 3 cores. Now, in multi-tenant, we've only got 1 set of background processes, 1 shared SGA, so we're going to take away 1 set of overheads, that was 1 core, leaving 6 cores for application processing. Now remember, in our previous calculation, we figured that we only needed 2 to support an application load. So now we can support 3 sets of applications in this consolidated server, twice as many cores, but 3 times as many applications. Very simple multi-tenant math. Now, if I took off my shoes and socks, which you might not appreciate, you can understand how perhaps with even bigger servers we can get more advantage with multi-tenant. And also remember that we started with an application server that was running at 60% load, which is actually pretty good. It wouldn't be at all unusual to see an application server running at 40% load. So we start right down here. We take away 1 core for the background, and now we're only really using 1 of those cores to support the application load. So this is how multi-tenant consolidation math works. So far what I've been talking about is our advantages in terms of capital expenses, consolidation of multiple applications onto a single server. And this delivers reduction in capital expenses because we can support more applications per server. I'm now going to move on to a discussion of our second key advantage with Oracle Multitenant, reduction in operating expenses. And this is the theme that we'll see as I move through these slides. First one here, one backup. Remember, from the applications point of view, it's the PDB that's the database, but from the operations point of view, it's the CDB that's the database. So now we've only got 1 backup to configure for all of the PDBs. All the PDBs benefit from this single backup, but we retain granular control, which in this case means that we could do a point-in-time recovery at the pluggable database level. Another example of managing many as one is configuring, let's say, Active Data Guard in a high availability environment. We have a production database and a standby database. Again, Data Guard is configured at the container database level. It's an operational concept. We have a single unified redo stream replicated from the production side to the standby side. So all of the pluggable databases plugged into the container on the production side benefit from this single redo stream. And as we add a new PDB in the production side, we have a corresponding PDB in the standby side, and just by virtue of being plugged into this environment in which ADG was already configured, your new PDB benefits from that environment. Now just think how difficult it was to do that in the prior architecture. You'd have to configure ADG from scratch. Here's another example, and this one might be upgrades. So in the case of an upgrade, again, this is an operational concept. We've got a new set of binaries. Perhaps we've got a new set of definitions of the Oracle metadata dictionary. So just by being plugged into this environment, we run an upgrade at the container database level. All of the pluggable databases are upgraded in one fell swoop, which is great. So here are several examples of operations which can now be performed at the CDB level, thus allowing us to manage many as one. And this is how we deliver the great reduction in operating expenses. But now I'm going to transition to the third advantage of multi-tenant. We've talked about reducing capital expenses. We've talked about reducing operating expenses. Now we're moving on to another theme, which is agility. Because if you think about upgrades, it's fine to be able to upgrade many as one, but that's not always practical. Sometimes you might not want to upgrade all of the applications for whatever reason. Perhaps one of them was dependent on a third-party application which hasn't yet been certified with a new version. Well, an alternative would be to create a second CDB. Let's call this version 12.x. And by unplugging our PDBs from the old environment and plugging them into the new environment, these PDBs are upgraded to the new version, 12.x. And you'll notice in this example, one of the PDBs stayed behind. For whatever reason, perhaps, it wasn't ready to be upgraded. So the theme here is that we can manage many as one, but retain granular control where necessary. And through this means, this granular control, we deliver great agility gains. Here's another example of agility. And in this case, we're talking about Oracle Real Application Clusters, or RAC. Back to what I was saying earlier. From the operations point of view, it's the CDB that's the database. So that follows, therefore, that when we configure RAC, Real Application Clusters, we do so at the CDB level. And in this example, I've moved to having multiple colors for PDBs. We've got 5 of them. And in this rather simple example, we have 2 nodes in our RAC cluster, node 1 and node 2. Within each node, we have an instance, CDB instance 1 and CDB instance 2, in nodes 1 and 2 respectively. But if you look in the nodes, in this rather simplistic example, you'll notice that there's only a subset of the PDBs open in each node. For example, in node 2, we only see red, blue, and purple, whereas in node 1, we see green, red, purple, and yellow. The objects at the top there that look rather like wine glasses are the secret to this. These represent the services, and it's the services that determine whether a database is available, a PDB is available in a specific node. So specifically to open a node, to open a PDB in a specific node, what we do is we open the services corresponding to that PDB in that node, and that's how the PDB is opened in that node in the cluster. Now this allows us to affinitize specific PDBs to specific nodes in the cluster, which is very important. It allows us to do horizontal scalability. It also allows us to partition the SGA virtually across the cluster. Now, if you look at the little resource meters here, what I'm trying to show in this example is that we have a very heavy processing load on this cluster for whatever reason at this stage in the business cycle. So to solve this, why don't we drop another node into the cluster and spread the processing load of the various PDBs across this newly expanded cluster, thus reducing the overall strain on the individual nodes. This is the sort of agility that we can deliver with Oracle Multitenant, and we really think it's unprecedented. In this particular example, my quip is that Oracle Multitenant makes RAC better, and RAC makes Oracle Multitenant better. It really is a very good symbiotic relationship. Now, another example of agility delivered by Oracle Multitenant can be illustrated here. In this example, we've got 3 different container databases, one for each of 3 different service level agreements, or SLA. So there's bronze, silver, and gold. And our little PDB starts life rather humbly down there in the bronze SLA, where you only have full backups, weekly full backups. Now, as the PDB's application becomes, let's say, more mission critical, we might want to move it up to a higher SLA. Now, with Oracle Multitenant, to do that is simply a requirement of unplugging the PDB and moving it to the higher level SLA. And in the silver level, we see daily incremental backups. And as before, we've got a PDB on the standby side, and there's the replicated redo stream, which we've seen previously. If we wanted to move to gold, it would be a similar operation. Unplug and plug into the new gold SLA CDB. This really is unprecedented flexibility delivered by Oracle Multitenant. Just think how hard this would be to do in a schema consolidated environment. Okay, another example of agility is provisioning. This is one of the major pain points for DBAs, and we address this extremely well in Multitenant. In database parlance, provisioning means creating new databases. And we do this in Oracle Multitenant through a process we call cloning. You can create a clone of a database locally within a given container. We call that a local clone. Or you can create a clone of a PDB from a remote container. We call this a remote clone. And in both cases, cloning is performed using SQL, as before. Cloning is an extremely fast operation. And here are some examples we ran. This was just an internal study we did on a Sun ZFS storage appliance. And we tried with various different sizes of database, fairly modest sized database, 24 gigs, all the way up to 1.3 terabytes, quite a respectable size. And you'll see on the right-hand side there some of the timings it took to run these. This wasn't an official benchmark, just an internal test. But a full clone of a 24 gigabyte database takes nearly 10 minutes and a little over 9 hours to do the 1.3 terabyte database. Not bad, but remember, this is good kit. Now, this is what we call a standard full clone. What we also have in Multitenant is what we call a snapshot clone. A snapshot clone takes advantage of copy on write capabilities, and it really is quite dramatic. Have a look at some of these numbers. Same sizes of databases, but if we look now at the 1.3 terabyte database, the time taken in the fifth column there to do the snap clone has moved down from a little over 9 hours to just about 6 minutes. That's incredibly fast performance. Taking a 1.3 terabyte database and creating a snapshot, a copy of that in 6 minutes. That's the time taken to get a cup of coffee. If your database isn't provisioned in the morning, you self-service provision this thing. By the time you've come back from the cafe, there is your database ready to be used. And what about storage? That column, number 2 there, 551, those are kilobytes. Kilobytes, that's half a meg of additional storage required to support a snapshot copy of this 1.3 terabyte database. So the joke we use here is that in multi-tenant math and snapshot math, 1 terabyte plus 1 terabyte equals 1 terabyte. It's almost negligible incremental storage. And these snapshot clones really happen remarkably quickly. What's the magic here? Well, let's think about how snapshot technology works. It's based on copying our files using copy on write technology. And this is how it works. Let's think about a file. What is a file? It's a collection of blocks and headers which point to those blocks. Now, traditionally, to create a copy of that, you simply copy all of the blocks and copy all of the headers. It's nice and simple, but it's inefficient. Now, with thin provisioning technology, we take a different approach to things. To take a copy of a file, rather than copying all the blocks, we simply copy all of the headers. It's much more efficient, and it involves minimal I/O to create this copy. It's only when you make a change to one of the blocks in the file that you then take the copy of that block, and then you repoint the header of the file in which the change was made to point to that changed block. All of the unchanged blocks, those headers remain unchanged. So for this reason, this technology is often called copy on write. We didn't invent this. We've built our snapshot clone technology on top of it. So if the underlying file system supports copy on write, we can perform snapshot clones. And in this way, we can deliver the performance that I just showed you. Okay, so we've been through some of the major advantages of the multi-tenant architecture. To review this architecture, we've got a single self-contained PDB for each application. Applications run unchanged. We deliver rapid provisioning through clones, and a pluggable database is a portable database. We have a single shared memory and set of background processes across the entire container database. That means that you can support more applications per server. And finally, common operations are performed at the CDB level, so you can manage many as one, but retain granular control when appropriate. Okay, now let's move on to a very important theme, which is how do you manage the shared resources in this consolidated environment? You don't want to have a single application running away with all the resources of the system. This is a goal we had here. Let's run through this at a high level. Let's say in this example we've got 3 PDBs, 3 applications, plugged into an environment where they have different priorities. So DW is low priority, CRM medium priority, and ERP, let's say, high priority. What we'd like to think is that if nothing else is going on, why not let the low priority system have access to all the resources in the environment? Why not? But when the higher priority CRM system comes online, we would expect it to take its fair share of resources and correspondingly have the lower priority system back off somewhat. And then as the top priority system comes in, we would expect the other 2 to back off considerably so that the top priority system has all the access appropriate. So this is what we wanted to achieve. And we've done so by extending Oracle Resource Manager. In Resource Manager with Database 12c, we can control CPU. In Exadata, we can control the I/O, sessions, and parallel execution servers. And we've got various different opportunities now with these new policies, which are defined in terms of caps and shares. It's very powerful, but it's a very simple set of concepts. Here's a simple example to take us through this. Again, let's say we've got 3 PDBs. And I show them here at the top, but in tabular form at the bottom there, HCM, let's give 2 shares to this one. And CRM and ERP will give each 1 share. So what this means is that HCM gets 2 out of 4. That means 50% of the shares. That means 50% guaranteed minimum CPU if it's required. And correspondingly, the other 2 have 25% guaranteed minimum of the CPU if they need it. But the column on the right-hand side, this is the cap column, this is the maximum. So without caps defined, that means that even the lower priority system can use up to 100% of the CPU if the other applications don't require it. This is what we call over-provisioning. And you might think that's a bad thing. It's actually a good thing. Over-provisioning is what allows us to take advantage of consolidation by sharing peaks and troughs in application load. Now, I'm sure you all want to upgrade to Oracle Multitenant now. How do you do it? Well, the good news is it's extremely easy. It's as easy as 1, 2, 3. Step 1, you upgrade the databases in place, simply by running the Oracle upgrade script as you always have done. So the various databases are updated in place and become what we call non-CDBs. This is Oracle Database 12c and non-CDB in the old architecture. You can stop there if you like, but I wouldn't recommend it. I'd recommend that you move to step 2. And step 2, you adopt these non-CDBs as PDBs by plugging them into a consolidated container database. So that's step 2. Step 3 is that you update your applications to work with Oracle Multitenant. But wait! I said that no application changes are required. So there is no step 3. Finally, let's talk about use cases. And here there are a very wide range of use cases, because this will eventually be the only architecture of the Oracle database, and as you'd expect, therefore, we need to be able to support the full range of use cases of the Oracle database. But here are just a few, and a great place to start is development and testing, for 2 reasons. First of all, by definition, it's not production. And second, the very engineers that you want to become expert in this new architecture are using it in their day-to-day operations. So a typical example here might be that you would take a full clone of a production database into a development container, and then individual test engineers will come through and provision, self-service provision perhaps, snapshot clones of that database. And you typically find that in the typical build cycle that every little build would require a minor upgrade to the schema, after which the golden master schema would be self-service cloned, self-service provision cloned for individual test and development engineers. So test and dev is a great place to start. Another great use case of multi-tenant is consolidation of disparate applications. These might typically be your tier 3 systems. These things are disproportionately expensive to manage, hidden away in various developers' desktops, possibly not patched or backed up, collectively representing arguably a very large risk to the organization. Now, why not consolidate all of these together, manage them much more efficiently, far fewer cores required, patch them regularly, back them up? This is the promise of Oracle Multitenant. So consolidation of disparate systems is an excellent use case. A third one might be database as a service. And here's the high-level goal of database as a service. In a self-service provisioning environment, you select from a standard set of sizes and a standard set of SLAs, and you'd like to have the desired PDB provisioned in your CDB of choice. And by the way, how about having that in minutes rather than months? And often it is months for organizations to provision databases. So the promise of provisioning of databases in Oracle Multitenant extremely rapidly is really dramatic. Here's that same example again, perhaps. In this case, we'll pick a large database, and we're going to run this one in the gold environment. As before, we see our PDB provisioned in the appropriate CDB. The fourth use case is software as a service. In this example, we have a single consolidated environment, which means that the provider only needs to manage one environment, but the individual tenants are all hosted in their own dedicated pluggable database. Consider the requirements. Tenant isolation. Well, each tenant is contained in his own self-contained PDB. You'd want security. Well, all native security features work. Encryption, redaction, database vault. How about ad hoc queries, reporting? All native Oracle tools work against the PDB. All of this is possible with Oracle Multitenant. But none of this is possible if the multi-tenancy is delivered in the application sphere. So Oracle Multitenant is a great platform for software as a service. Another example is what I call data mule. And here's a specific example of data mule. Let's talk about an application vendor. And think about that all-important first impression. What happens when you first get this new shiny application, you download the software or plug in the DVD even, and then you go through this lengthy process to set up and configure this application. And that can be rather tedious and error-prone, and quite often that first impression is not a favorable one. Well, a better way of doing things then might be for the vendor to deliver the application as a PDB. So on their side, they configure a PDB with the application on it. They literally unplug it, stick it in an envelope, ship it to the customer, who opens the envelope. It's like Christmas. Plug that PDB into a container database at their level, and there, voila, is an application up and running, ready to go. So maybe it's not 17 steps to one, but a dramatic reduction in the number of steps required to configure this application. And you can think of many different examples of this data mule use case, using a pluggable database as a vehicle for moving large quantities of data, if you like, at road speed rather than internet speed from one location to another. So here are the examples, and of course there are many others, many other use cases we see for Oracle Multitenant. We have great support for Oracle Multitenant. Even though this was only released on June 25th, 2013, we already have a great ecosystem of partners, a number of famous names on this slide, and there are many others as well. But let me finish by reviewing the great advantages of Oracle Multitenant. And there are 4 key advantages. We reduce capital expenses because we can host more applications per server. We reduce operating expenses because of the ability to manage many as one, deliver standardized procedures and service levels, and our support for development of cloning and in development and testing. We can maximize agility by rapid provisioning, through portability with pluggability, and scalability in real application clusters. And very importantly, it's easy to adopt because no application changes are required. So thank you for your attention. This is Oracle Multitenant, a new architecture with Oracle Database 12c.